Hi guys, Dr. Diaz again. Okay, look at this one. Magnetic field between two parallel conductors. Look what's going to happen. Oh well, first of all, look at the equation of the magnetic field now. B is equal to mu naught I divided by 2 pi r. Oh, where are all these crazy equations coming from? We're going to discuss this in a second. But here are some examples that are going to show you though why they use this magnetic field. You remember those trains in Japan that it travels like 500 kilometers per hour, or almost 400 miles per hour? Well, those trains are moving in this kind of rail that it creates a magnetic field, and it moves toward what sometimes people call magnetic levitation. It's because, you know, the magnetic field, they have the same polarization, same side, like N and N, they will have magnetic repulsion. And the magnetic repulsion is so strong that, you know, these trains that are tons, they all look like they're floating there, and they can move at high speed. It's actually pretty efficient, conserve a lot of energy and fuel. But you know, you have to be careful because sometimes when they crash, 500 kilometers per hour is actually a pretty nasty number. So let's go here. Oh, the principle also behind this, you know, those doors, I mean those banks door that they put all the money above it, whatever is that, they use some sort of like the magnetic field thing idea, right? When they put those things, and they have also show magnetic attraction, that thing's so strong that it's almost impossible to open the door by yourself. You have to turn off the polarization in order to the door to open. And I'm sure some of you have played with magnets, and when you put, you know, the N and S together and then you try to separate, then you probably have to put a lot of force there because it's actually get very stuck there. The same thing, magnetic field there, it's actually pretty intense. And it's going to be a little bit difficult to take off. Now let's look at this example before we go and study something else. Aha, here it is. Consider two straight parallel wires separated with distance A, and each carrying a steady current I. So here we have. So this one here will generate a magnetic field that's going to affect the second wire. Also, the second wire is going to generate a magnetic field that's going to interfere with the first wire. So the thing will be here, how do we calculate the force, or find the force of this? Well, before we do this, there's an expression for force that I've been discussed there. If you remember the force that we discussed so far, was this one. Force is equal to charge, velocity, and magnetic field. But there's another equation that you probably saw when we saw the right hand rule, that it says something with the current and magnetic field. So where that equation is coming from? Well, this actually is the same as I current, the length of the wire times the magnetic field. Well, because look here, these equations here, and this actually, I would say, is butchering here calculus a little bit, but if you look here, V is the same as the derivative of the position with respect of time. Yeah. And suppose that instead of X you call it L, because we're looking here for length. So this will be dL dt. Now we have this expression that says QV, so we can put QV. So it's going to be what? Q dL dt. Now if you put Q inside of this thing, like d dt of Q and L, well, it could happen because the current, I mean the charge, when it depends on time, that's actually current, right? Because dq dt is actually current. And assume that the length is the same as constant, but then in this case, this product is going to give you the product rule. L is constant, you take it out, it's going to be L, and then you would end up with something like dq dt, but dq dt by definition is current, I, and that's why this equation I gets here from dq dt, and L gets here because it's a constant. So these two equations are equivalent. The other thing is, this one works perfectly when you have particles. This one works perfectly when you have a wire and there's current going through it, right? When there's current, you have a wire, there's current going there, we know the current is going to be charged per second. There's charge moving there. But you have a gazillion of those, and you have all them moving along the wire. So in that case, you would use this one. But when you have a particle, like one proton, one electron moving in a magnetic field, then you would use this part of the equation. Okay, so using this one because we're talking about, using this one because we're talking about wires, right? We're talking about why we use this one. We're talking about electric, one charge alone, a proton or electron, you use this one. Now, since we're working with wires, we're going to use this one, and the equation is going to look something like this. Oh, look at that. Now it's very complicated. Why is that then? Because look, here it's telling you that the force, first, if you remember the equation we would write in there a moment ago, let me see if I can write it here. Force is equal to ILB. But the force due on the first wire, we have 1, and we know the L is the same. This magnetic field is going to be due to the second wire. And if you find the force due to the second wire, which is going to be I2L, remember the length is going to be the same, that magnetic field is going to be due to the first wire. That's why it appears here. There's a 2 for F1, and if you saw the other way around, it's going to be, for F2, it's going to be then a 1 due to the first wire. Right, so in other words, we have a wire, something like this. Okay, let me draw it here. Current moving this direction, and there the magnetic field here produced is going to be due, if they have a second wire, and suppose they move in the same direction, the magnetic field of 1, this one, let's say 1, is going to be due to the second wire. In the magnetic field of the second wire is going to be due to the first wire. Okay, look here. Basically, we will end up with an equation like this, and this is an equation to rewrite. We're writing here the equation of force per unit length. So if you send L the other side, you have L here, you have the equation for force. Now look here. Most of the time, L is going to be constant or something. Usually they give you a numerical value like it's 1, and then you're done. Now you know I is current, right? I1 and I2 is current. I1 is the current goes through the first wire. I2 is the current goes to the second wire. A is the distance between these two wires, right? From here to here, this is A. And L is the length of the wire, right? The length of the wire. But what is mu? What is mu naught? Here it is. Permeability. It's the degree of magnetization that a material obtains in response to an applied magnetic field, and is in this value. It's 4 pi times 10 to the minus 7 newtons ampere squared, or 1.257 10 to the minus 6 newtons ampere squared, or 1.257 times 10 to the minus 6 Tesla meter ampere. Okay, so actually these are the same numbers that you multiply by 4 pi, and then, well, here instead of using Newton, we can use Tesla. We can do the conversions here. Oh, look at this one. What happened? This is interesting. Parallel wires with covering in the same direction attract each other. So if they're going in the same direction, they attract each other. This will be the way that you use to close the door from when you put your money in the bank. That thing, very strong, it will get stuck together. When they go in different directions, they will have some kind of magnetic repulsion. It will be the one that is used in those trains in Japan. Okay, so let's see other thing here. Okay, when the current moves in opposite direction, the magnetic field will reverse it. Yeah, okay, and the wires repel each other. Okay, parallel conductors, same direction, attract. Parallel conductors, current opposite direction, repulsion. And this example, we're going to do it in a second because I need more time and space for doing this one. So wait in a second.